There we go. All right, this is an intro to chapter 9, and it's called One Proportion Confidence Intervals. So our goal here is to find an interval to estimate I can spell here. The true population proportion from a sample proportion. Okay, so what am I saying? Find the interval to estimate the true population proportion from a sample. Well, usually we don't know about populations, and we oftentimes want to know. Like, for example, let's say in this case, I'm interested in knowing what percent of the population has a student loan that they're still paying on. So, example, what percent, and that's another word for proportion, what percent of the population still pays on a student loan. Well, how could I estimate that? Well, what we've done in the past is we've said, hey, let's just take a sample. Okay, so take a sample. Take a random sample of n equals 100, and further suppose problems writing on the screen here. Suppose we find that 37 have a loan. Well, this information would give me what we call p hat for my sample proportion would be 37 out of 100, which would be 0.37 or 37%. Right? So is this a good estimate for the population proportion? Can I safely say that, of all Americans, adults, 37%, approximately 37% have a student loan? It's like, well, if I get a different sample, am I going to get a slightly different number? Probably. I'm going to get 39 or 35 or 40. It's probably going to be close to 37, I would think. But we want to be a little more precise than one number. And so we want to find an interval. Okay, and an interval is like a range of numbers. I want to say, hey, I think the true population percent is between 35 and 40. And I'm pretty confident of that. That's where we're heading. Question is, how in the world do we figure this out? Well, let's go back to something called the p-hat distribution. Okay, and the p-hat distribution is this. Normal curve, the center of it, use of p-hat is p. This is the population proportion. Equals a proportion of all adults who have a loan. And the standard deviation is the square root of PQ over N. Right? And so when I take a sample, this might be a sample here. Here's another sample. Here's another sample, right? These are sample percents. This one might be 37. This one might be 39%. This one might be 29% or something like that, right? These are all samples, but they're all going to be close to the true population proportion. If the true population proportion was 35, then I would expect to get a bunch of samples close to 35, right? I wouldn't expect to get them way out here at 40 or way down here at 25 or something. Okay, so that's the idea. We're going to use this. And we're going to use this idea here. For 95% of the samples, actually, I'm not, it's a bad way to start that. 95% of the samples lie within 2 standard deviations of the mean, which is p in this case. In other words, 95% of all p hats lie within 2 standard deviations of p. Right? That's what we did. We've got that because this curve is normal. And remember, this is normal because of the condition NP is bigger than 10 and NQ is bigger than 10. Okay? So as long as this is a normal curve, which we're going to assume that this is the case, okay, 95% of all p hats lie within 2 standard deviations of p. Now, I'm going to do a little different color here, and we're just a little aside. Okay. If Joey is within 6 feet of Susie, then of course Susie is within 6 feet of Joey. Alright, does that make sense? So hopefully it does. If I'm within 5 feet of you, you're within 5 feet of me. Okay? So let's continue on now. We're saying 95% of all p hats lie within 2 standard deviations of p. So if this is Joey here, and this is Susie here, I can switch them. Right? So for 95% of p hats, p lies within 2 standard deviations of p hat. Okay, does that make sense? Okay. 95% of p hats, all p hats lie within 2 standard deviations, because if here's 1 standard deviation and here's 2, 95% are in the middle. Okay, but that also means that p lies within 2 standard deviations of p hat, right? Okay, because if Joey's within 6 feet of Susie, Susie's within 6 feet of Joey, p is that close to p hat, just like p hat is that close to p. Okay, so let's see what that says. That means p is between p hat minus 2 standard deviations and p hat plus 2 standard deviations. Right? These are just numbers. So p is between those. For, I'm going to keep track of this, for 95% of p hats. Okay. Let's try to shorten this up a little bit. That is, p is between p hat plus or minus 2 standard deviations, right? The plus or minus is just combining these, the plus here and minus and the plus here. Well, good news is we know what the standard deviation formula is. It's right up here, right? So that means P is between P hat plus or minus 2 times the square root of PQ over N. Problem, I don't know what P and Q are, because P is my population proportion, which I don't know what it is. I just have my one sample. So we're going to use what we call the standard error, right? That is the standard error. Oops. Not quite the standard deviation, but it's pretty close. It's our best estimate for it. So P is in this interval for 95% of P hats. Okay, and because of that, we call this a 95% confidence interval for P, and that'd be P hat plus or minus 2 square root of P hat Q hat over N. Now, I kind of did something here that we talked about this a long time ago, and I used this fact. I used the 68, 95, 99.7 rule, right? Well, I probably wasn't completely honest with you, because 95% of the population is not really within 2 standard deviations. Remember, this is 68% within 1 standard deviation, within 2, within 3. It's really 95% is within 1.96 standard deviations. And that's really close to 2, so that's why we use 2. And we're just using this for an estimate anyway, the 68, 95, 97. But we want to try to be a little bit more precise. So instead of saying 2, I'm going to use 1.96. In fact, well, let's leave it at that for right now, because we're going to change that, because this is specifically for 95%. What if I want a 99.7% confidence interval, or a 90%? Well, for this problem, let's say this. For student loans, we have P hat is, what do we say? P hat was 37%. So we got 0.37 plus or minus 1.96 square root of 0.37, and Q hat is the complement of that, 0.63 over N was 100. And if I do 0.37 plus that and 0.37 minus that, I will get my interval. So let's go ahead and do that. Okay, we get 0.275 and 0.465, and if I write that in percents, it's going to be 27.5% and 46.5%. Okay, so what are we saying? We're saying I'm 95% confident that P, the true proportion of people with a student loan is between 27.5% and 46.5%. So I'm pretty confident, right, that it's in that range. Okay. Now let's ask the question: is that a good thing Well, yeah, 95% confidence is pretty good, but your confidence and my confidence don't necessarily mean the same thing, do they? I might be really confident of something and you wouldn't be. So let's define, what does confidence mean? Okay. 95% confidence means that for 95% of the samples, remember, for 95% of my samples, P is in this interval. Now notice though, for each sample, I'm going to get a different P hat, right? One sample I might get P hat is 37. The next sample P hat might be 39. And so this interval here will be different for each sample. Okay? So let's just kind of make a note of that. Different sample gives a different interval. So for 95% of the samples, let's see, 95% confidence means that for 95% of the samples, P sorry about this. P will lie in the interval formed. Right? 95% confidence means that for 95% of the samples, P will lie in the interval formed. Noting, and notice each sample gives a different interval, right? So I know if I take a sample, I can find the interval, and 95% of those intervals will contain the true population proportion. So let me draw a picture here, and then we'll close with that picture here. Let's go back to my curve here. Where P is here. Here's one standard deviation. Here's two standard deviations. So if I pick a P hat, right, this is the P hat distribution. Thinking my battery's going bad here. So if I pick a P hat here, could be here, and if I go two standard deviations, which that's this length right here, each way, P is in it. If I pick another one over here, I go two standard deviations each way, there's my interval, P is still in it. See, here's P. Now, it's possible that I pick a sample way over here, right? And if I go two standard deviations this way, right, here's two, it's not going to quite make it there. So P will miss this interval. But how often does that happen? Well, 95% are in between here. So only 5% on the outside. So 95% of my samples, another way we'll do this, 95% of samples will give an interval that contains P. Okay. Last thing on this, when we're talking about it, is we did a 95% confidence interval. Oops. And that's where we used 1.96. Well, what if I want a 90% or a 99% confidence interval? Come up with a different formula, or let's adjust the formula, I should say. So a 1 proportion Z interval we'll call it P hat plus or minus Z star square root of P hat q hat over n, it's a q, where z star is what we call the critical value, and that's equal to 1.96 for a 95% interval. It's 1.645 for a 90% interval, and it's 2.576 for a 99% interval. And these are at the bottom of our t-table, as we've done in class. Okay, so here's my 1 prop z interval. And in order to use this, what are our conditions? Our conditions that have to be met are: 1, we have to have a random sample. Because if our sample isn't random, then it can't represent the population at all. So random sample. And then secondly, NP has to be bigger, NP hat has to be bigger than 10, and NQ hat has to be bigger than 10, because that's what ensures that is normal. Okay, I'm going to get my pen squared away, but I think that's a good start for one proportion z intervals.